Okay, the most important point on the oxygen set curve is the point of lowest concentration. Okay, because this point represents the maximum impact on the dissolved oxygen due to wastewater discharge. Okay, this point is known as critical deficit, which is DC. And the time of travel to this point is known as critical time, TC. So TC is calculated using this formula, K1 over K2, so times L naught exponential negative K1 TC. So this one is actually the equation that you have learned from chapter 2, previous lecture note. Okay, while critical time TC is given by this equation in your textbook will be equation 3.23. Okay, so you can see in the graph here. Okay, so this is the point of the most important point. So you need to determine DC and also TC. So once you determine TC, you can know what is the distance at any time or any distance of the stream. Okay, and DO is actually initial dissolved oxygen, where you can calculate this using the formula later I will describe in the example. Okay, this example is actually the same example in 3.3 in your book. Okay, applying the BOD set curve. Okay, so if we put the question, translate the question into a diagram. Okay, so actually you have a stream A and there's a wastewater stream that will meet together at this point. Okay, so you want to calculate all the parameters at P and to sketch the oxygen set curve for this point, right? So given to you, the wastewater found to have maximum flow rate 15,000 meter cube per day. Okay, this is actually the flow rate of your wastewater stream is meter cube per day. You need to convert it, okay, into meter per second. And then given also BOD5 is equals to 40 milligram per liter of, this is the parameter for the wastewater stream. And then the DO concentration is 2 milligram per liter at temperature of 25 degrees C. So later you will see that the stream, the upstream from the point of wastewater discharge, okay, we're talking about the point in A here, have a flow rate of 0.5 meter cube per second. The BOD5 is 3 milligram per liter and the dissolved oxygen is 8 milligram per liter at 22 degrees C. So you will see there are two different temperature, which is A is 22, the condition at the wastewater is actually 25 degrees C. Okay, so we need to find the the average, the mean temperature, the mean Q for the stream B. Okay, for the condition at B. Okay, and then complete missing of the wastewater stream is almost instantaneous. Okay, given to you the velocity after the meeting is actually 0.2. Okay, so the aeration constant given is 0.4 day. So this is K value at 20 degrees C. Okay, so we need to find or we need to sketch a oxygen set curve profile for 100 kilometer. Alright. Okay, so your end answer will be something like this. You will need to produce a sketch of oxygen set curve. Okay, so you need to determine the one that I circle in the red circle, you need to determine the TC or XC, okay, and then the question asks for 100 kilometer distance, so maybe you can break it into 50 kilometer, 75 kilometer, and 100 kilometer. So before we can do this kind of curve, we need to find first the DO value, which is the initial deficit, and also the deficit T, okay, and also we need to determine TC in order to make the profile of the oxygen sac. Okay, before we can proceed with the producing the oxygen sac curve, okay, first we need to determine the characteristic of wastewater stream mixture. Okay, in this point, if we look into the diagram, we are actually wanted to determine the condition or the characteristic of this part. Okay, which is the part after the wastewater stream meet here, right? Okay, so okay, the first one we wanted to calculate what is uh, the Q mix after the stream A and the wastewater stream meet. Okay, in order to do that, okay, so it's like your mass balance. So A plus W, okay, will equals to B, right? So first you need to convert this 15,000 meter cube per day to meter cube per second, and then total up is the sum of the flow rate. Okay, so you will get 0.67 meter cube per second for the Q mix here. Okay, whereas for to determine the BOD at the mix point, okay, so this is given in equation 3.1. You can refer equation 3.1 from your textbook. So actually, in the end, you will get the BOD in the condition of P is 12.4, right? And then you calculate the ultimate BOD. Okay, so this ultimate BOD is actually you can use from equation 2.2 in your textbook. We have learned this one in previous lecture note, okay, on calculating the ultimate BOD, right? Okay, for the dissolved oxygen mix, okay. So this again, you can use equation 3.1, okay, to calculate the DO mix, okay. If you're lost, have a look in page 91, okay. So it is actually the same way of calculating the O mix and also T mix is like average. You will use the equation that's similar to this one. It's just finding pro rate, okay. So in the end, we will see that the average T mix for stream B is actually 22.8. Okay, because just now we have a different temperature, right? This is 25 degree, and the stream A is I think around 22 degree. So stream B will be 22.8 degree. Since from the earlier calculation, we get the value of temperature at the mix point is around 22.8. So we need to do a correction for reaction constant, okay, at 22.8. So we need to find a new value for K1 and also K2, right? Okay, here is from for K1, we calculate it using Van Hoff Arrhenius equation. So we insert the value of temperature 22.8 here using theta equals to 1.047. Okay, so you will get your K1 is actually 0.26. Okay, so this is actually at the condition at point B. Okay, so for K2, we use the same equation, right? So the theta would be 1.016. Okay, so you replace the theta and temperature 22.8, and then you get the value of K2 is equal to 0.42. Then we calculate the critical deficit temperature, okay, um, using the Streeter and Pelf equation, right? So here, where equation 3.23, use equation 3.23 to calculate TC. Okay, after you get the value K1 and also K2. However, you need to determine first the DO, initial oxygen deficit. Okay, so you can determine the value of DO by referring to appendix in your textbook. So it will be in appendix C, table C3, equilibrium concentration milligram per liter of dissolved oxygen as a function of temperature. So although it's the column rate chloride concentration in milligram per liter, so you refer to the column with zero concentration of chloride. So and then you go to temperature at 22.8 is along 22 to 23. So it will give you somewhere in between 8.68 to 8.83. So we get around 8.69. Okay, so with the value of DO, K1, K2 at 22.8, you can calculate TC. So you get TC is around 2.5 days. Okay, so once you calculate TC, you can get the distance of critical deficit. Okay, so here you can use the equation earlier where um, in equation 3.21 where T is equal to X over U, where X is your distance, U is the velocity. So given in the question, the value of your velocity is around, after the mixture, is around 0.2 meter per second. So by replacing T is equals to 2.5, and then the velocity of 0.2 meter per second, you will get the distance X is 43.2 kilometer. Okay, so this is one kind of example how you can you can plot your sketch or plot your oxygen set curve. Okay, so if you look further in your textbook, okay, so the example give you to calculate the condition at certain point, okay, which is at 20, 75 and 100 kilometer from the point of discharge. So you may use the equation T equals to X over U in order to determine the new value of T at 20, T at 75 and T at 100. Okay. Okay, so that's it. That's the end of our chapter water purification process in natural system. So